All right, let's get to graphing trig functions. So we're going to start with the basics. We're going to graph y equals sine x, y equals cosine x, y equals tangent of x. And I'm also going to introduce y equals cosecant x, and y equals secant x, and y equals cotangent of x. All right, so let's start off just kind of getting to know this unit circle, because that's going to play a big role. If you don't really understand the unit circle, and what these actual values mean, then it's going to be very tough to translate it into your engineering projects or whatever you're going to be using these equations for. Right? You have to understand when to use these equations, or they're completely useless to us. All right. So let's start off by talking about. Here's the unit circle. At an angle of 0 in standard form, that's this angle right along the x-axis here. Okay, and that crosses right at this point right here. Well, what is the height of that point? Well, the height of that point is 0. That's the y value. What is the distance to the right of the y-axis? Well, that is 1. Okay, so we know that the cosine of the angle 0 must be 1, and the sine of the angle 0 must be 0, because the sine is just the height, which is also the y value, and the cosine is just the distance to the right, which is also the x value. So every x and y value, if you're on the unit circle, is also just the sine of that angle of the angle that goes through them. All right, so at an angle of 0, we know that we have sine of 0 is equal to 0. All right, the next angle we're going to talk about is pi by 6, which you guys you used to think about as 30 degrees, but we're now going to think of it as pi by 6. If you make a 30-degree angle here, then this guy will go straight through the unit circle at a height of 0.5, and so the sine must be 0.5. So on the graph, we'll go to pi by 6, and we'll go up to 0.5 right there. All right, the next important angle is pi by 4, so we'll draw an angle of pi by 4, and we will see that it cuts right through 1 over root 2. So if a person or something is going along this circle, by the time it gets to this angle of pi by 4, it's going to be at a height of 1 over root 2, and so the sine of pi by 4 is 1 over root 2. The next angle is pi by 3, and it crosses the unit circle at a height of root 3 over 2, which is about right here. I want you to also notice on the bottom here, see how we got 1, 2, 3, 4, 5, 6. These x's, each spot that I'm talking, this represents root, so pi by 6, pi by 4, pi by 3, and this is going to be pi by 2. Notice you have groups of 3 here. So this is all the 3 different angles within each quadrant, and then these black dots here are your 0, pi by 2, 3 pi by 2, and pi. So 0, pi by 2, pi, 3 pi by 2, and 2 pi. All right, so you see how they don't line up perfectly, because pi is like 3.14. It's not exactly 3. 2 pi is 6.28-ish, not exactly. So none of these are right on the money in terms of these natural numbers. But it kind of gives you an idea that radians are really just numbers between 0 and 6.28. Not 0 between 360 degrees like what you're used to. All right, the next dot's going to be at pi by 2. It crosses at a height of 1. So at pi by 2, we get a height of 1. At 2 pi by 3, we have a height of root 3 over 2. At 3 pi by 4, we have a height of 1 over root 2. 5 pi by 6 gives us a height of 1/2. And at 2 pi, there's a height of 0, right on the x-axis. And we can just continue along with all of those points. You got 7 pi by 6, you got 5 pi by 4, and so on and so forth. And of course you got all the angles in between, which will make a nice smooth sinusoidal curve where the lowest is -1, the highest is +1, and it just keeps going up and down. All right, in the same way, let's draw the cosine function. At angle 0, we'll go here, and the distance to the right is 1. And so we start off, angle 0 gives you a value of 1. The next angle is pi by 6, which hits the unit circle right here at a distance of √3/2 to the right. And so, since that distance to the right is √3/2, we graph √3/2. The next is pi by 4, and the distance to the right in this case is 1/√2. Notice that that's the same as its height, so the sine and the cosine will be the same at that spot. Pi by 3 cuts the unit circle at a distance of just 0.5 to the right. So pi by 3, we have 0.5. And next we have pi by 2 straight up. And so the distance to the right is nothing at all, so we are right on the x-axis. 2 pi by 3 brings us into negative territory. It is a distance of 0.5 to the left. So 2 pi by 3, which is right here, brings us down to -0.5. 3 pi by 4 is -1/√2 to the left. 5 pi by 6 is √3/2 to the left, so -√3/2. Pi is as far to the left as you can get, -1. And as the angle moves along, it gets closer and closer to the y-axis, and then farther and farther away in the positive. And of course, those aren't the only angles, they're just the main ones, so all the other angles count. So we will fill in the rest of this curve. You probably noticed that this is the cos curve and the sine curve are basically the same curve. It's just with a shift of pi by 2 over. So honestly, when I do word problems, I pretty much never use a cos curve. I just always use a sine curve. So cos curve could, depending on how you think about things, some people could just exclusively use the cos curve. Some people could go back and forth depending on whether you're talking about things being up and down or left and right. But for me, I just always use a sine curve. You do whatever you prefer. The next function I want to talk about is the tangent function. Right, the tangent function, now there are a couple ways of looking at it. A lot of people look at it as it's just going to be the sine function divided by the cosine function, which is true. It's going to be every value. Like for example, sine here is 0 and cos is 1, so the tan is just going to be 0/1. So here the sine is √3 divided by 2, so √3/2. Here the cosine is 1/2, and so the tan will be √3/2 divided by 1/2, which is just √3. You're probably also curious to know what happens right here. We have the sine is 1 and the cosine is 0. That happens right at pi by 2. And in that case, 1 divided by 0 doesn't exist, so the tan of pi by 2 actually doesn't exist. If you put tan pi by 2 in your calculator, you should get like an unknown value, like it would say error or whatever it says on your calculator. But I'm going to look at this in a way that seems it'll be more useful in real practice. So at an angle of 0 degrees, we know that the sine of the angle is 0 and the cosine of the angle is 1. The tangent of the angle is 0/1, but that is also the slope of this curve. So another way to look at it, instead of just looking at it as sine x over cosine x, we could also look at it as delta y, right? The distance between, so this is 0, 0 to 1, 0. We could look at it as delta y, which is 0 divided by 1, which is still 0. So right here, the tan is equal to 0. Right? Now you go to the next spot, and you can say, okay, well the sine is 0.5, the cosine is √3/2, and so that's just going to equal 1/√3. And that's true, but also, if you notice, the slope is just delta y over delta x. Well, since 0.5 is your delta y, and so √3/2 is your delta x, if you go from 0, 0 to this point, well then it's also just your slope. So literally the tan of any angle is just the slope of the curve on the unit circle. Right, so we've got a slope here of 1 over root 3. 1 over root 3 is about 0.577. At pi by 4, well, it has a slope of 1, right? The delta y over delta x is just 1 over root 2 divided by 1 over root 2, so it's just 1. So pi by 4, we should be at 1 right here. At pi by 3, well, now delta y over delta x is so root 3 over 2 divided by 1/2, and so we get about 1.732. It's exactly root 3. And so we got 1.246 way up here, right? And as you get closer and closer to pi by 2, you'll see that the height increases closer and closer to 1. But what happens when you get the lower part, so the cos of x is approaching 0? What happens when something approaches 0 and the top does not approach 0? Well, you're going to start getting, so sine is going to be positive, because it's above the x-axis. Cos is going to be still positive because it's to the right of the y-axis, but it's getting really, really small. Well, this is just going to blow up. And so right at pi by 2, it's going to be undefined, but this guy will go higher and higher and higher and higher, right? And of course, the slope, as you can see, is getting closer and closer to straight up and down, like that. Now another fun way to look at the slope is if you draw a line right at x equals 1 here, it's interesting that since now we're leaving x equals 1, if you were to continue all of these angles right through, well then your delta y over delta x for the same angle is going to be, delta y is going to be whatever this height is, and delta x is going to be just 1. Right? And so wherever this thing touches this line, that is also its slope. Right? So some people, I used to call this the tan line. I thought I was funny at the time. I wasn't, still am not. But if you do like an angle of 80 degrees, well, where is it going to hit that tan line? Boom, way up here. Okay, so the tan of 80 is about 9.003. So it's way up there. It's way, way, way up there. Okay. So as you can see, there are lots of different ways of looking at this. There's like, you can look at it as just the value of sine divided by the value of cos. You can look at it as the slope of the curve on the unit circle, or you could look at it as when you have of the line on the unit circle at that angle, or you could look at it as wherever it hits that wall that's one to the right of that angle. All right. Now, what happens when you go beyond pi by 2? What happens when you go just to the left of pi by 2? Right, so let's go to 2 pi by 3 here. Now we know that the height is root 3 over 2, and the distance is now negative. It's going to be negative 1/2, and so your answer is negative root 3, so that's about negative 1.7 something. So there's 1, 2, 4, 6, 1.7 something right about here. Okay, but I kind of skipped over. What happens when I'm just beyond here? Right, well this, where does it hit that? Where does it hit that tan line, let's say? Oh, well, it kind of goes way down here. It's actually in the negatives. It's almost at negative infinity. Right? And as you can see, sine over cos, sine of x, on this angle here, sine is really close to 1, but cos is really close to 0, but in the negatives. Sine is positive because it's above the x-axis. Cos is negative because it's to the left. Okay? And so you're going to end up with negative almost infinity on this side. And it's going to come down. Okay? Now, as you can see by the symmetry here, the slope going this way and the slope going that way will be the same slope, but this one will be negative because it's going down. This one will be positive because it's going up. Also, the sine on both sides is going to be the same, and the cosine is going to be the same, but one's going to be negative of the other. So anywhere you look at it, oh, also it crosses this tan line up here, but on the other side it crosses the tan line down here, just negative of the same distance. So anyway you slice it, it's going to be all the same values, but it's going to be negative, right? So it's going to come up, we're going to be exactly at 1 here. 1 over root 3 here, which is, it's about 0.577. And once we get to exactly pi, now the sine is 0, the cosine is -1. Well, 0 over -1 is simply 0. So it crosses right here. But also, the slope, as you can see, is 0 because it's a straight line across. You start going down again. Now the sine is negative and the cosine is negative. If they're both negative, then the tan should be positive, and sure enough, it hits this tan line at a positive rate, and the slope is positive. And it is let's say the sine here is -1/2. The cos is negative root 3 over 2. -1/2 divided by negative root 3 over 2 is positive 1 over root 3, which is about 0.577. So 2, 4, 6, right about here. Okay, here we're going to get 1, right, at an angle of 5 pi by 4. They're both sine and cos are going to be -1 over root 2. So you get 1. At 4 pi by 3, you're going to get sine is negative root 3 over 2. Cosine is -1/2. So you're going to get root 3, which is going to be about here. And it's going to keep going up. And when you finally get to 3 pi by 2, right here, now the sine is -1, the cosine is 0. Well, -1 over 0 is undefined. You have yourself another asymptote. There you go. And this is the look of it. What happens just beyond? Oh, well, now sine is still negative because it's below the x-axis, but cos is now positive. So now we're going to get negative numbers. And it's going to go from -infinity, and it's going to keep following that same pattern. It's going to go up right through here, and it's going to continue along in the same way. Right, and of course the tan of 2 pi, no matter how you look at it, sine is 0, cosine is 1, so 0 over 1 is 0. You could also say an angle of 2 pi is going straight to the right, which has a slope of 0, and you could also say that it hits the tan line at a height of 0. So interestingly, if you notice the sine curve, we had a period of 2 pi. The cosine curve has a period of 2 pi, it's just shifted. It's just the sine curve shifted a little bit. And the tan curve actually has a period of pi, because since it is the slope, you have a positive slope, you have a negative slope, then you have a positive slope again, all the same slopes, and then you have a negative again. You could also look at it as sine over cos. Well, when sine and cos are both positive, tan will be positive. When sine is positive but cos is negative, well, now tan is going to be negative, but all the same values. And when they're both negative, well, sine over cos is going to be the same as sine over cos when they were both positive, because it's going to be a positive value. And when sine is negative because it's below, and cos is positive because it's to the right, you're going to have the same values as when sine was positive and cos was negative. Okay. And so it does have a period of 2 pi, but since it repeats, it's actually a period of pi. Now, another cool thing with the tan function is even if you made this circle bigger, like that, it doesn't really have to be the unit circle. If you make the circle bigger, the place where it touches that outer circle, well, the slope hasn't changed at all. And sine over cos will still be the same. Sine will be bigger, but cos will be bigger, but they'll both be bigger by the same factors. And so you'll end up with the same thing. So for the tan function, it's interesting. If I ever gave you a problem like, hey, there's a guy going around a Ferris wheel, and after 17 seconds, what is the slope of the curve from the origin to him there? So like if they put a ramp to that person right there, what would be the slope of that ramp? Okay, well, the slope would easily just be the tan of that angle. Okay, so the tan of the angle will just is actually literally giving you the slope at any point on an angle around a circle. So you can see already how that would be super useful in mechanics and in engineering. All right, now we're going to talk about the reciprocal functions. So the secondary, we have the primary trigonometric functions we talked about, and now we're going to talk about the secondary trig functions. Now these secondary trig functions are just the reciprocal of the primaries. So the reciprocal of y equals sine x is y equals cosecant x. Right? So that means we'll just go along the x-axis when sine, like when x is 0. Okay, so when the angle is 0 degrees or the 0 radians, the sine, as we know, is equal to 0. The sine of 0 radians is equal to 0. So cosecant, which is the reciprocal of that, will be equal to, so we say cosecant of 0 radians is equal to 1 over 0. Ooh, but that is undefined, so we're going to have to back that up. We cannot say 1 over 0. We're going to have to say this is undefined. Okay, so we have no value here. Right there for cosecant. All right, what about at here? At pi by 6. Okay, the sine is equal to 0.5, so the cosecant must be equal, so the cosecant of pi by 6 must be equal to 1 over 0.5, which equals 2. All right, so we will graph a 2 there. There's 1, 2, right up here. All right, what about at pi by 4? At pi by 4, we know that sine of pi by 4 we know equals 1 over root 2. So the cosecant of pi by 4 must equal root 2 over 1. So root 2 at about 1.4. All right, so right here we get about 1 right here. A point right about there. Okay, but another way to do it is if you just look at the sine curve here, you can already see where everything's going to end up. If you just kind of look at this sine curve, this blue curve along here, you can say, well, I know that when it equals 0, that its reciprocal will not exist. But when it's just a little bit bigger than 0, like at an angle of like 0.00001, right? Well, the sine is a very, very small number, so 1 over a very small number is a very, very large number. So we know it's going to approach infinity there. It's going to be an asymptote. We've seen a lot of those in our time, and it's going to come down like this. And as sine gets bigger, the reciprocal gets smaller. Now, at exactly pi by 2, the sine of pi by 2 is equal to 1. So if the sine of pi by 2 equals 1, then the cosecant of pi by 2 must equal 1 over 1, which is 1 as well. So at that point, they're actually exactly the same value. It's going to come down to there. Now sine starts going down again, perfectly symmetrical. And when it gets to 0, we know that cosecant will not exist. So we're going to have another asymptote. So it goes all the way back up. Okay, so you guys should remember from our reciprocal functions, there we go, this, it's going to go through about there, this goes through about there, that's about right. Okay, you guys should remember from our reciprocal function section earlier that when a function equals 1, its reciprocal also equals 1. When a function is below 1, which is always the case for sine x, well, below or equal, well, then the other one will be above. So these guys will never go below, between 0 and 1, they'll always be above because the reciprocal was always below. And as approaches 0, the other one approaches infinity. Okay, what happens just beyond pi? What happens over here? Well, this is where sine goes from positive down to negative, right? So now the cosecant will also go from positive to negative because 1 over a positive number is positive, 1 over a negative number is negative. But just beyond pi, sine is a very, very small negative number. So cosecant will be a very, very large negative number. Right? So it comes from the other side of the asymptote. Okay, the closer you are to pi on the wrong side of pi, so just a little bit more than pi, the larger cosecant is. Because if sine is very, very close to 0, cosecant is very, very close to infinity. All right, so as sine gets lower and lower, that means larger and larger negatively, cosecant gets higher and higher. And we'll reach right here. You're going to be at 2 because sine is at negative 1/2 right here. So cosecant will be at negative 2. Right here, sine is at negative root 3 over 2. So cosine will be at negative 2 over root 3. So that's at about 1.15. And then it's going to come in. And when sine of 3 pi by 2, that's the lowest sine. Well, the sine of 3 pi by 2 is negative 1. That's the lowest that gets. Well, when it's negative 1, cosecant will also be negative 1 because 1 over negative 1 is still negative 1. And then the sine of the angle will go back towards 0, so it gets smaller but negatively, which means cosecant will get larger but negatively, all the way until we get back to 2 pi. And at 2 pi, sine of 2 pi is 0. Well, then cosecant of 2 pi is approaching negative infinity, and there's an asymptote there. Okay, that's when sine switches from negative to positive, and so will cosecant, and so cosecant will come again from the other side. So you can see that cosecant is periodic. It has a period of 2 pi, and it just kind of does these like a U shape up here and an upside down U shape down there. I've heard a lot of students be tempted to call them like quadratics or parabolas. They are not the shape of a parabola. We know the shape of a parabola is as you go. It's kind of like x squared. If you graph it, it'll be a different shape. But I guess I could see why people would think it looks like that shape for sure. All right. So and it'll never, like we said, cosecant will never go between negative 1 and 1 because sine never goes above 1 or below negative 1. Sine is in this area only, so cosecant will be only outside of that area. But they do touch right at those tips. They are the same value at those tips. So at pi by 2 and at negative pi by 2. All right, now we're going to talk about secant of x. So y equals secant of x. Right, now secant is very similar to cosecant in the same way that cosine is very similar to sine. Right, so secant is just 1 over cosine. Right, so whatever value, whenever you get an angle, so here the cosine is 0.866, well at that same angle of pi by 6, the secant will just be 1 divided by 0.866. To be more specific, since cosine of pi by 6 equals root 3 over 2, well then the secant of pi by 6 is equal to 2 over root 3, the reciprocal. All right, we already know that's about 1.15, so I might as well throw that one in there now. All right, so let's start at angle 0. At angle 0, cosine is already equal to 1. Well, what's 1 over 1? Well, 1 over 1 is just 1. So that means that the cosine of 0 is 1, but also the secant of 0 is 1. Now, as you see, cosine starts at 1, but it goes down to 0 by the time it gets to pi by 2. Well, what happens to secant when you get down to 0, or when you get up to pi by 2? Well, the secant, which is just 1 over the cosine, well, since 1 over 0 is undefined, well, we know that we cannot have a value for secant x at pi by 2. But what happens when you're just a little bit in front of it? Well, the cosine is still a little bit positive. It's just a little bit to the right of the y-axis. So it's a small, very, very, very small positive number. Well, if it's a very small positive number, then 1 over a very small positive number, let's say 1 over 0.00001 is equal to, it's going to be, say, 1, 2, 3, 4, 5, 10, 100,000. It's a huge number. Okay, so what happens is this guy ends up going up, approaching infinity. Let's see here, I know it's 1/2, so here 1 over 1/2 is about 2. Here I know we're 1 over root 2, so this is going to be root 2, which is about 1.7. It's going to go kind of like that. There we go. All right, what happens on the other side of pi by 2? So when you're beyond pi by 2, now cos is in the negatives, which means secant has to be in the negatives. And when it's going to start off, cos is going to start off very small. It's going to be negative a little bit, and it's going to go all the way to -1. So that means cosecant is going to start off very large in the negatives. It's going to go all the way until it hits -1. But then cosine will start getting back smaller because it's getting closer to the y-axis, still negative. Secant will get larger, still negative. And as you can see, it's very similar to what we just did with cosecant, except now it is with secant. So the idea is if you can just easily draw the cosine curve like this, well then you just kind of, for the secant curve, you just kind of put the 1 where the 1 is and go up instead of down, and just kind of touch. They're just going to be touching, the hill and the crest are just going to be touching each other like that. Perfect. Last but not least, we're also going to have to graph cotangent. Well, cotangent is just 1 over tangent. So let's just graph this one the exact same way as what we did with reciprocals. We know it's going to be the reciprocal. Cotangent is going to be the reciprocal of tan. So I'm just going to look at the tan graph, and then we're just going to figure out what the cotangent graph will look like. Okay, so I'm just going to look at the graph. Here I see that tan is equal to 0, because it's tan of 0 is equal to 0. So that means that cotangent will have an asymptote there, or at least it won't exist there. Now, just beyond that, tan is a little bit positive. So if tan is positive, then cotangent must be positive because they are reciprocals of each other. But since it's very, very, very small, cotangent will be very, very, very large. When tan hits 1, which is right at pi by 4, because that's when sine and cos are the same, and remember tan is just sine over cos, well, cotangent is just cos over sine at every point. Well, if sine over cos is equal to 1, then cos over sine is also equal to 1. 1 over 1 is still equal to 1. There you go. And then as tan gets larger, cotangent gets smaller. Right to here. When tan goes off towards infinity, that's when cotangent reaches 0 or approaches 0. Okay. Now tan goes into the negatives. Negative a very large number. Well, that's because cotangent is negative a very small number. Right here at 1, 2, so 3 pi by 4, that's when tangent equals 1. Well, then that must be when cotangent equals 1. Sorry, I should say -1 for both of those because the cosine is negative and the tangent is negative and cotangent is negative. Tangent is negative because it has a negative slope. Cosine is negative because it's to the left of the y-axis. Right here we've got tangent is, let's say, is sine over cos. That's going to be 1/2 over negative root 3 over 2. It's about 1 over root 3 right here. Again, -1 over root 3, I should have said. And so cotangent will be negative root 3 over 1. What's root 3? About 1.7, so 2, 4, 6, right about here. Right, so Sine over cos at that angle is 1/2 over negative root 3 over 2. So cos of a sine will be negative root 3 over 1, and which is about negative 1.7-ish, right about there. All right, and as tangent gets closer and closer to 0, cotangent of those angles will be going down closer and closer to negative infinity, still in the negatives. Okay, now all of a sudden, tangent of pi is 0, and so that means the cotangent is 1 over 0, or undefined, and then the tangent actually goes back into the positives. So just beyond pi, both sine and cosine are negative, which makes tan positive, or you can just say the slope of any of these line segments in the third quadrant are all positive. So it goes into the positive. So cotangent must also be positive, because 1 over positive is positive. When tan is small, cotangent is large. When tan finally hits 1, cotangent will hit 1. Tan keeps going up higher, so cotangent keeps going down lower, and tan eventually will be undefined, and that's where cotangent is 0. Tan is now in the negatives, well, so is cotangent. Tan is large negatives, cotangent is small negative. Tan finally hits 1, or sorry, negative 1, and that means cotangent hits negative 1, and then tan goes closer to 0. Once it hits 0, cotangent has another asymptote. That's at 2 pi. All right, there you have it. So as you can see, tan is periodic over 180 degrees, or you can say over pi of a period of pi. Well, then cotangent also periodic from a period pi. And you look, it's kind of like a mirror. They're just kind of mirrors of each other, right? So cotangent, you could easily build cotangent once you know tangent. Okay, there you have it. Those are the graphs of your 3 primary trig functions and your 3 secondary trig functions.